In this video, we're going to discuss the relationships between angular and linear quantities, which fundamentally comes back to our definition of a radian. We have our angle theta measured in radians was the arc length divided by the radius. This meant that the arc length was equal to the radius times the angle when measured in radians. So what this says is that the distance it actually traveled, the arc length, was equal to the radius times its angular displacement, which made sense as we have something. Let's say that we have this here. If it was on the far outside of the radius, then it moved farther than if it were in closer, it didn't move nearly as far. So our definition of the linear velocity, or more specifically the tangential velocity, follows the same relationship here. So as shown in this figure, this is the velocity at a point on the edge of the curve here, and this is actually a tangential velocity, so vt. And by tangential, the definition of tangential is that it is perpendicular to a radial line. So perpendicular to the radius is the tangent. So the tangential velocity, this is the linear speed of this point right here out on the edge, is the tangential velocity is vt for tangential, is the radius times the angular velocity. So we can see here that as we move farther out on the radius, we're going to have a larger speed, which makes sense. If we have a point maybe halfway along the radius, this is going to have a smaller linear speed, a smaller tangential velocity, because it has a smaller radius. If we go to a point all the way at the center of the circle, then the radius is equal to 0, and this has no linear speed. It's just simply rotating in a circle. It has no linear speed associated with it. So the tangential velocity, the velocity tangent to any point on the curve, is the radius times the angular velocity. This is the definition of the tangential velocity. And the units of this are in meters per second. So essentially the radians disappear. And if you remember back, the radians do disappear because the units of the arc length would have been in meters, and the units of the radius would also have been in meters. So theta is actually a unitless, or a radian is actually a unitless dimension. So we just kind of hold it there, so that way we know that we're talking about an angle as a ratio of arc length to radius instead of some other unit of measure. So the units of the tangential velocity, the units of the radius would be in meters, and the units of the angular velocity would be in radians per second. This only works if we have it in radians per second, by the way. And then so this is going to be meters per second are our units for the tangential velocity. Similarly, we can talk about a tangential acceleration. Now this would be, I know previously we looked at things going in uniform circular motion, so the speed didn't change, but now that we have torques and things, we can speed them up as they go in circles. So this is the tangential acceleration. This tangential acceleration, this is at. This is again perpendicular to a radial line, so the tangential acceleration would be in the same direction as the tangential velocity, parallel or anti-parallel, one of the two. So this would go into either speeding up the rotation, speeding up the speed of it as it goes around a circle, or slowing it down. And the definition of the tangential velocity, so we call this at for tangential, sorry, not velocity but acceleration. Tangential acceleration would be your radius times your angular acceleration. And again, following the same reasoning behind why the units of tangential velocity were meters per second, the units of the tangential acceleration are meters per second squared. This is because the radians kind of fall away. So the tangential acceleration is the radius times your angular acceleration. So we have here basically your linear quantity is your radius times your angular quantity. So s is equal to r theta. This means your linear displacement is the radius times your angular displacement. Tangential velocity is the radius times angular velocity, and tangential acceleration is your radius times your angular acceleration. So you see here, like in this figure, tangential acceleration is the same direction as the tangential velocity, and the tangential acceleration affects the magnitude, but that's not to say that we don't still have the centripetal acceleration that we had previously for something going in circular motion. So we still have a centripetal acceleration, and the centripetal acceleration is still defined the same way it was before. This is equal to the speed squared divided by the radius. But using our new definition of the speed, which is, this would be the tangential speed, this is going to be r omega squared divided by r, because after all, we have the tangential velocity is equal to r omega. So then this becomes r squared omega squared over r, which is over r, which is then just equal to r omega squared. So we have a new definition for centripetal acceleration. The centripetal acceleration is equal to v squared over r, which is equal to 4 pi squared r, should use the same r here, 4 pi squared r over t squared, where t is the period, or it is also equal to r omega squared. So we have all of these as definitions for our centripetal acceleration. And now that we have acceleration in two directions for an object rotating around. Previously, we always had uniform circular motion, so we only had centripetal acceleration, but now we have a tangential acceleration as well as a centripetal acceleration. And the centripetal, also known as the radial acceleration, always went along a radial line, and the tangential acceleration always goes along a tangent line. And by definition, the tangent line is perpendicular to a radial line, and so we actually have perpendicular components of acceleration. So solving this triangle, we can have just following the same way that we've solved vectors previously, the total magnitude of the acceleration would be the square root of the sum of the square root of the sum of the squares of its components. So our magnitude of the acceleration would be equal to the square root of the tangential acceleration squared plus the centripetal acceleration squared. And this is because these are two components of the same thing. This is, call that the x component and the y component. Okay, so the total magnitude of our acceleration, now we need to take in consideration both components of it. So just for another little example here, a motorcycle accelerating, he hits the gas here and it accelerates the wheels. The drive shaft goes to accelerate the wheels, and there is some angular acceleration of these wheels. Well, these angular accelerations then apply a tangential acceleration on the ground, right? Or they apply a force to get this acceleration. Then there's a reaction to this through Newton's third law, an action-reaction pair, and there is then therefore a tangential acceleration of the motorcycle forward, which is the same as the magnitude of the tangential acceleration that the wheels apply on the ground, or that they feel on the outside of the wheels there. So here we have it. Basically, in order to go from an angular or rotational quantity to a linear one, you just take the rotational quantity and multiply it by the radius, and you get your linear quantity.